That can be you if you don't come review limits with me right now. Hi everyone, welcome to the channel. My name is Shani Harris and today we'll be reviewing limits of a function. So the first thing we would have to remind ourselves is, what is a limit? The limits of a function is simply the number that the function approaches as x approaches some number. So for example, if we have a function y, while x is probably approaching 0, y might be approaching 1. Therefore, 1 would be the limit of that function. And we can write this as the limit of y x approaches 0 is equal to 1. So while x approaches 0, y is approaching 1, and 1 is therefore the limit of that function y. Okay, so the next thing is considering the side that x is approaching some number from. So x could be approaching a number from the left, or x could be approaching a number from the right. So once x is approaching a number from the left, the limit that you would receive is called the left-hand limit. And while x is approaching some number from the right, the limit you would receive is the right-hand limit. So in order for a limit of a function to be considered defined, aka exists, the left-hand limit and the right-hand limit has to be the same. They have to be equal. And the best way to explain this is with a graph. So this is the graph that we're working with. As I was saying before, we would have to consider x from either side, whether it's the left side or the right-hand side. So here, the number that x is approaching is 0. X could be approaching 0 from the left, or x could be approaching 0 from the right. So if we're trying to find the left-hand limit, we'd go to the left end, and as x is kind of getting closer and closer to 0, we would see the graphing of y as a path until we reach the limit. So x is getting closer to 0, therefore y is getting closer to something as well. We don't know that number, but we're going to find that out. So x is getting closer to 0. As close as x can get to 0 is the closer y can get to 1. And that's for the left-hand limit. For the right-hand limit, it's the same procedure. You go to the right end, and as x is getting closer to 0, we see the graphing as a path we take. So x is getting closer to 0. We see the graphing as a path. We realize that, as x is approaching 0 from the right, y is approaching 1. And that would be the answer for the limits. So for the left-hand limit, you realize that the number that x is approaching, you would have this superscript, a minus sign as a superscript. And for the right-hand limit, you would have a plus sign as a superscript for the number that x is approaching. And we got 1 as both of the answers. So since left-hand limits and the right-hand limits are equal, the same, the limits of the function overall is defined. It exists. So if we got a different answer for the right-hand limit, for example, let's say 2. I'm gonna say the 2. So if we got 2, that means that the limits of the function wouldn't exist. It would be undefined. So the next thing is evaluating limits. So this is when you're not given a graph. And one of the main methods you use is direct substitution. So for example, if you have a limit of a function 3x squared plus 5, and x is approaching 2, just 2. You can simply find the limit of this function by substituting 2 in the expression. So you would have the 3, you put 2 wherever you see x, so you have 2 squared plus 5, and that would be equal to 3 times 4, because 2 squared is 4, plus 5. 3 times 4 is 12, plus 5, and then you would have your limit as 17. So we have noted direct substitution as a method to evaluate limits. That's the first method you go to. However, it doesn't work in all cases, and this is an example. So if we're supposed to substitute 3 into this expression, you would have 3 squared minus 9 over 3 minus 3, where you would get 9 minus 9 over 3 minus 3, where you eventually get 0 over 0. And this is what we would call indeterminate. It doesn't mean that the limit is undefined, it doesn't exist, but it means that you'd have to go to different methods, like for example factorization, in order to determine the limit. Basically kind of like finding the equivalent expression to this, and that's what we will be doing right now. We have the expression x squared minus 9 over x minus 3. We would have to find a way to like kind of factorize this, and we'll basically see where it goes. So we have x squared minus 9 in the numerator. So this we can identify as the difference between two squares. Why? Because we have x being squared and 9 can be written as 3 squared as well. There's a minus sign. And with the difference between two squares, you just simply write it as the square root of each term. So you have x and 3, and it would be the product of them with like the opposite signs in between them. Yeah, and then we would have the denominator, x minus 3. So from here, you realize that there's an x minus 3 in the numerator and an x minus 3 in the denominator. And since this is a product, this means that we could simply cancel out the x minus 3, and we would be left with x plus 3. So this would mean that the limit as x approaches 3, the limit of x squared minus 9, x minus 3, as x approaches 3, would be equal to the limit of x plus 3. I'm gonna write this better over here. X plus 3 as x approaches 3. And from here, we can use direct substitution. So we have limit x plus 3 as x approaches 3 is equal to 3 plus 3, and 3 plus 3 we know is 6. So we'll be reviewing the laws that are involved in limits. So this is the first one. So if you are trying to find the limit of a function, which is basically a constant, it doesn't matter what number that x is approaching, you're going to get back the same constant. So for example, if you're trying to find the limit of 3 as x approaches 2, the limit will still be 3. The limit is going to be 3. And this is because the graph of any constant is simply a straight horizontal line that goes through that number. So it doesn't even matter what number that x is approaching from the left or from the right. Here's another law in limits. So we have the limit of f of x as x approaches a, and the limit of g of x as x approaches a, right? And we want to find what is the sum or difference between these two limits. This law is basically telling us that if these two limits are approaching the same number, we can write it as one term rather than separate clause. And since we know what is the result of these two limits, what are the limits, we could just have it simplified like this. The product and the quotient is similar to the sum and the difference in the sense that you're basically like, instead of writing it separately like this, you could just join the two into one bracket once they're approaching, x is approaching the same number. So this is the product. You have the limit of f of x as x approaches a times the limit of g of x as x approaches a. So this would be equal to the limit of f of x, the limit of f of x times g of x as x approaches a is equal to this. And the same thing goes with the quotient. So that brings us down to our final law in limits. So let's say that we have a function, we have the limit of a function as x approaches a being m. F of x limit as x approaches a is m. And we have some number. We included a number that's being multiplied by that same function basically. All this is saying is that you could just bring out the number to not be included as the limit. And once you know the limit of f of x as x approaches a, like we do, the limit is m, we could just times the two. So we'll times the k and the m to get the result. Now we move on to infinity and limits. So how do we evaluate a limit of a function where x is approaching infinity? So you know the first step that we always take when we're trying to evaluate a limit is to direct substitute. Once you realize direct substitution doesn't work, you can think about other methods. But right here, we would put infinity in wherever we say x. And when we do that, we're going to eventually end up with infinity over infinity. And we would call that indeterminate. So just like how we saw 0 over 0 as indeterminate, the same case goes for here. That doesn't mean that the limit of the function is undefined or it doesn't exist. It simply means that we would have to go to other methods to evaluate it. So to go about evaluating the limits of a function where x is approaching infinity is that we'll divide each term in the numerator and in the denominator by the variable with the highest power. So in this case, x is the variable with the highest power. X is the variable, and we're looking for where exactly x has the highest power. From here, you're going to see that x with the highest power is x cubed. So that is what we're going to do. We're going to divide each term by x cubed. So we'll have a 2x cubed over x cubed minus 7 squared over x cubed plus 5 over x cubed all over 3x cubed over x cubed plus 2x over x cubed plus 1. And from here we can see the plus 1 should be 1 over x cubed. So my bad, guys, carry on. We can simplify. So we have a 2x cubed divided by x cubed. That would cancel out each other. X cubed would cancel out each other, leave us with 2. Minus 7x squared over x cubed would leave us with 7 over x, because basically the 2x squared would like cancel out. Like we're basically cancel out the 2x, not the 2x, the x squared, and that would leave us with that x in the denominator. So yeah, this can't be simplified anymore. Here the x cubed would cancel out each other, plus we'll have 2 over x squared plus 1 over x cubed. And the next step, since we simplified everything, the next step would be direct substitution. So now we can put, wherever we see x, we can put infinity there. So we'll have 2 minus 7 over infinity plus 5 over infinity cubed all over 3 plus 2 over infinity squared plus 1 over infinity cubed. So from here, 7 being divided by infinity. So we'll have a smaller number being divided by a larger number. What would that give us? 0. Because how many times can infinity go into 7? 0. So we're going to have 0. Same thing goes for the 5 over infinity cubed, because infinity cubed would simply be infinity. You can't get much larger than infinity. So yeah, so we're going to have the plus 0. Move to the denominator, I have the 3 plus 2 being divided by infinity squared. That would be 0, and 1 divided by infinity cubed would be 0. So from here, the answer would be 2 over 3. So that would be the limit of this function. We now move on to the special cases of limits, and that would involve sine and cosine. So the first one is that the limit of sine ax over ax as x approaches 0 is equal to 1. And similarly, the limit of ax over sine ax as x approaches 0 is equal to 1. And this is where a is any number but 0. So if we're supposed to have like a as 0 in the expression, basically, so we'll have a sine 0 times x, that would leave us with sine 0, and then we'd have 0 times x, that would be 0. So we'd eventually end up with 0 over 0, and we know that is indeterminate. So this is the special case, and this is the other special case involving cosine. So we have the limit of cos ax minus 1 over ax is as x approaches 0 is equal to 0, and 1 minus cos ax over ax as x approaches 0 is equal to 0. And just like this is where a is not equal to 0. So here's an example that we're going to do. So we have the limit of sine 5x over x as x approaches 0, and we're trying to find it. So recall the special case that the limit of sine ax over ax as x approaches 0 is equal to 1, and this is where a is not equal to 0. So from this, we can use this case in order to solve this. However, we'll have to recall that a in the numerator has to be the same a in the denominator. So just like here, we have 5. However, in front of the x, basically we'll have 1. So we'd have to get the sine 5x over x to be in a similar form as this, so we can use this case to solve it. And how do we do that? All we have to do is basically multiply the denominator by the 5, and whatever you do in the denominator you have to do in the numerator too. So let me just write it out first. So 5x over x as x approaches 0. Yeah, what we're doing is that we're multiplying the denominator by 5, and since we multiply the denominator by 5, we could just multiply the numerator by 5 because we'll have to make it balance at the end of the day. And since we're doing that, let me just write it better. Yeah, this is 5x over 5x. Since we have a 5 right here, if you recall from one of the rules, one of the laws that we went through, where we had the limit of k f of x as x approaches some number, let's say a, can be written as k limit of f of x. Yeah. So that being said, we can simply just bring the 5 in front of the limit, basically. So we would have, ooh, this is kind of auto. Okay, we had 5 limit of sine 5x over 5x, and put that back. And there we can use this special case because the a in the numerator is basically the same. So we have the 5 there and the 5 there. It looks the same, so we can just use the special case. So this limit we know would be equal to 1 from the case, and we just multiply by the 5, and therefore we would get 5 as the limit of this function. So this is our next question. We're trying to find the limit of 1 minus cos 1/3 x over 4x as x approaches 0. So with this question, recall the special case that the limit as x approaches 0 for 1 minus cos ax over ax is equal to 0. So we want to find a way to have this function to basically resemble this, where we have the same number being in front of the x. So right now we have 1/3 being in front of the x in the numerator and 4 being in front of the x in the denominator. So we'll have to get it to the same number. So what I would like to do, I would like to go to the denominator and try to get the denominator to be the same number as the one in the numerator. Because, yeah. So we want to know what number times 4. So m is some number. We want to know what number times 4 gives us 1/3. So from here, I'm going to cross multiply. So we have 12m equal 1. Therefore, that number must be 12. So we're meant to say 1 over 12. We're going to multiply the denominator, basically, by 1 over 12. So we can get 1/3 in the same, so we can get 1/3, 1/3 to be in front of the x. And remember, whatever we do for the denominator, we'll have to do it for the numerator, so the function can basically stay the same. So that's what we're going to do. Write back the limit of as x approaches 0, 1 minus cos 1/3 x over 1 over 12 times 4x. Whatever we do in the denominator, we have to do it in the numerator. So I'm gonna just put the 1 over 12 right here in the numerator, basically. Let's put that in brackets. So that would be equal to the limit as x approaches 0. We would have the 1/3 in the denominator, 1/3 x, and in the numerator, basically I'm gonna leave the 1 over 12 and still have the same thing. 3x, 1 over 3 x. So from here, similar to the other question, we're going to bring the 1 over 12 in front of the limit. So because that's a rule we can use, so we can just have this expression, so we can basically apply the special case. So we're going to have the 1 over 12 in front of the limit. So we're gonna have limit as x approaches 0 for 1 minus cos, probably put this in bracket, well, no, actually, 1 minus cos 1/3 x, I hope you can see, over 1/3 x. And for this expression, basically, just put the multiplication sign, this would be equal to 0 because we're using the special case. The a, basically the number in front of x, is the same, so we can use the special case, and this would be equal to 0. So we're gonna have 0 times the 1/12, and that would give us 0. So the limit for this function is 0. Our next question is finding the limit of sine 7x over sine 2x as x approaches 0. So sine 7x over sine 2x can also be written as like a separate, since it's one fraction, we can separate the two terms in the sense that we're writing sine 7x over 1 times 1 over sine 2x. And once we write it like that, we're going to try to manipulate it to get one of the special cases. So since we have not even one, but in this case both, and you're going to see why. So you realize that we have sine 7x over 1. In order for this to match this, we would have to have 7x in the denominator. And all we're going to do is that we're going to multiply the denominator by 7x. So that's what we're going to do. So let's say times 1 over 7x. So we can get the 7x in the denominator. However, what we do to the denominator, we'll also have to do to the numerator. So I'm going to multiply the numerator by the 7x. We'll move on to the second term, basically. We'll have 1 over sine 2x. And we want to try to get the 2x in the numerator. So all we have to do, I'm going to write back the 1 over sine 2x. All we have to do is that we multiply the numerator by the 2x. And whatever we do to the numerator, we also have to do to the denominator. So I'm going to put the 2x under here. Because at the end of the day, it's a product. You're multiplying. It doesn't matter what order you put it in. You're still going to get the same answer. So here we have it. I'm going to simplify this so we can see this more clearly. X approaching 0. 7x over 2x. We're going to have sine 7x over 7x times 2x over sine 2x. So if you recall earlier in the video, one of the laws that are involved in limits is that when you have a number in front of like a function, basically, you can bring out the number to be, you can bring out the term, the number, to be in front of the limit. So that's what we're going to do. We'll have the 7x over 2x. Then we're going to have the limit as x approaches 0 for sine 7x over 7x times 2x over sine 2x. And from here, what we can do is separate the two limits. So as I was saying before, you separate the two limits, basically, the two functions. And then we go from there. We can use the special cases now. We can apply it. So we'd have the 7x over 2x. The limit as x approaches 0, sine 7x over 7x would simply be 1. And the limit as x approaches 0, 2x over sine 2x would simply be 1 as well. So there we have it. So the x's would cancel out each other. And for the limit, we're left with 7 over 2. And that would be the limit for the function sine 7x over sine 2x as x approaches 0. Here's the final question we're going to do. So we're trying to find the limit of tan x over x as x approaches 0. So to solve this, to evaluate this limit, we have to recall that tan x is equal to sine x over cos x. So where we see tan x, we're going to put sine x over cos x and see where it goes. So here we have the limit as x approaches 0 for sine x over cos x, and that would be over x. So next thing, what I'm going to do, I'm going to write this more clear, this expression more clear, because we want to see what we're doing. So we have limit of x as x approaches 0 for sine x over cos x. since this term is being divided by x, basically we can write it like that, and when it's being divided by x, we know we can also write it as the reciprocal multiplied by the reciprocal of x. Next thing is that just like in the previous question, one of the previous questions where we had the sine 7x over sine 2x, and we basically separated the fraction, that is what we're going to do with the sine x over cos x. So we're gonna have the limit as x approaches 0 for sine x over 1 times 1 over cos x over x. So for this, we want to use the special cases. Basically, we're trying to find a way to use the special cases. So we'll have the sine x. This kind of resembles the special case where, let me just write it down, the limit of as x approaches 0 for sine ax over ax, where a is not equal to 0. So we can try to get the sine x over 1 to this form basically, and in order to get it into that form, we would have to get x in the denominator, and we could simply do that by multiplying the denominator by x. However, we have 1 over x right here. I have 1 over x right here. So guys, so what I'm gonna do, I'm just going to bring the 1 over x, I'm going to join these two fractions together. So I'm gonna have the sine x over x times 1 over cos x. Yeah. Next thing, since I have this, what I'm going to do right here is that I'm going to treat these two as separate limits using the law involving the product, where we basically separate the two. As x approaches 0 for sine x over x being multiplied by the limit as x approaches 0 for 1 over cos x. So for this one, we know that this from the special case, this is going to be equal to 1 multiplied by, for this, what we do is that we're going to use direct substitution. So we have x approaching 0. All we do is that we're going to basically substitute 0 into the expression. So we're going to have 1 over cos 0, and that would be equal to 1 over 1. So that would just be 1, basically. So yeah, let me just erase that. So we know for that limit, that would be 1. So we'll have 1 being times by 1. Therefore, the answer would simply be 1.